Hello everyone, my name is Zon Quinn and my advisor is Dr. Swadesh Mukusentra. My project is about the effect of hydrogen peroxide treatment on manganese-doped zinc sulfide core shell fluorescent quantum dots. This presentation will include what are quantum dots, specifically the zinc sulfide manganese zinc sulfide quantum dots, motivation behind this project, purpose and hypothesis, experimental method, characterization with UV-vis, fluorescent, and XPS, antimicrobial study using minimum inhibitory concentration assay, cytotoxicity study using human dermal fibroblast cells, conclusion, and further study. What are quantum dots? Quantum dots are very small particles, about 2 to 20 nanometer in size, with unique optical and electronic properties. They are often referred to as zero-dimension semiconductor nanoparticles or artificial atoms. They differ from their bulk counterparts in a way that they have high surface to volume ratio, so we could modify their surface by attaching ligands, which is very useful for biological application. And they also exhibit the size-dependent fluorescent properties. This can be seen in the picture here. With decreasing size in the quantum dots, there is a larger band gap energy. So the band gap energy is the energy difference between valence band and conduction band. And their fluorescent emission shifts to a shorter wavelength. This size-dependent emission is an attractive property since the band gap energy can be tuned by controlling their size. The zinc sulfide manganese zinc sulfide quantum dots. So this is the notation to write that this is manganese doped zinc sulfide core with zinc sulfide shell quantum dots. This is a widely studied material due to their fluorescent property used in bioimaging. The manganese dopant gives orange fluorescent emission, which is a good contrast against biological fluorescent, which is green color. These quantum dots can be synthesized at room temperature using water in oil microemulsion synthesis. The manganese by itself does not give fluorescence because its electronic transition is prohibited. So by doping inside the zinc sulfide serves as an absorption center. So when the UV light with 320 nanometer wavelength hits the quantum dot, electron is excited from ground state to excited state in zinc sulfide, and it creates a hole in the ground state. So this hole moves to the ground state of manganese, and this excited electron from here jumps to the excited state of manganese. When this excited electron relaxes back into the hole, it emits light with 590 nanometer wavelength, which is an orange color emission. So doping allows color tunability for these highly efficient luminescent materials. Manganese dopant sits near the surface of the quantum dots. So the system we're using is about 1.6 mole% doped. So which means that every 200 zinc sulfide molecules, there are about 3 manganese ions. And the surface defect can cause this excited electron to be lost to the environment. So material with a large band gap energy are often used to passivate the core. So to trap these excited electrons and form shell. So this is zinc sulfide shell in this case. Motivation for this project was that our lab has developed systemic bactericides, that is zinc oxide-based nanomaterial, called zincoside to control citrus screening. So the zinc oxide can be converted to zinc hydroxide, which then breaks into zinc ion and hydroxide ion. So this zinc ion causes toxicity. The problem is that it lacks the fluorescent property, so they cannot be tracked to understand their pharmacokinetics and dynamics. To track, we need a model system and wanted to use zinc sulfide manganese zinc sulfide as our model system. Zinc sulfide can be oxidized to zinc sulfate. So this is a soluble salt, so provides a free ion for killing the bacteria that will best mimic this zinc oxide. The purpose is to use known optically trackable quantum dots, make it antimicrobial to serve as a surrogate to study their translocation in plant. We hypothesized that antimicrobial property can be achieved by oxidizing the surface with strong oxidizing agent. The method we use is water in oil microemulsion synthesis, also known as reverse micelle synthesis. The first step is to synthesize that manganese dope fluorescent quantum dots, the zinc sulfide quantum dots. I'm showing you here the experimental setup of microemulsion synthesis. We are creating reverse micelle system in each flask with respective dispersed ion. So this picture here depicts reverse micelle. You can see three components. Here, the aqueous medium with ions dissolved is getting surrounded by the surfactant, so hydrophilic head with hydrophobic tail inside the organic solvent. One miss, these cut ion collides with the anion and they coalesce, create a quantum dots, the size of which is limited by the size of the reverse micelle, so which in turn can be controlled by ratio between organic solvent, surfactant, and aqueous solutions. So we first mix this zinc sulfide manganese source with the sulfur to create manganese dope zinc sulfide core. It has excess sulfur, and then we added zinc, only zinc, to form that zinc sulfide shell. So we got this. The next step is to oxidize this surface to achieve antimicrobial efficacy. And we chose the hydrogen peroxide to oxidize the shell since it is a strong oxidizing agent. This step took multiple trial and error because the goal is to still preserve the fluorescence while also oxidizing it. And now we're finally able to present these three samples. We will call it HPT for hydrogen peroxide treated, have sample 1, 2, and 3, and 1 has the lowest peroxide concentration. So this ratio indicates the molar ratio between metallic zinc and hydrogen peroxide. With each sample, there is twofold increase in the hydrogen peroxide concentration. So this oxidation process occurs in microemulsion medium. After the synthesis, we have to purify them because the application is an aqueous medium. So we study on the purified sample, we study their characteristic. On purified sample, this is the UV vis data taken. We are observing for the change in characteristic if the chemical reaction converted zinc sulfide to zinc sulfate. Here, the control is observing at 324 nanometer, and we see a consistent decrease in the UV vis band maxima towards the blue region with increasing peroxide concentration. This means that the band gap is increasing since zinc sulfate has a lower band gap energy than zinc sulfide. This trend indicates that peroxide is treating the surface, is oxidizing the surface. Here we study their fluorescence. The data is taken with concentration adjusted so we can compare their intensity. This is what we visually see under UV lamp. The orange color fluorescence is due to the manganese dopant and corresponds to emission peak at 590 nanometer. Least peroxide treated sample, the HPT1, is showing higher fluorescence than control. We also confirm this in the spectrum where we see that HPT1 and 2 both show higher fluorescence than control. Whereas the HPT3 manganese emission peak has completely quenched. It might have been oxidized so much that their outer surface is completely gone and exposed manganese, so which becomes unprotected for radiative realizations to occur. Since it doesn't show fluorescence anymore, it is not a preferred model system, but we chose this sample to study XPS since the effect might be most pronounced on that one. So here are the XPS data. We're looking at zinc, oxygen, and sulfur peaks. Both zinc and oxygen show similar peak in both control and HPT3 samples, but there is a pronounced difference in sulfur peak. We compare their peak to the binding energy value obtained from thermoscientific XPS databases. Peroxide oxidized sample shows sulfate peak at 168 electron volt compared to sulfide peak at 161 in control. Therefore, we confirm the oxidation of sulfur into sulfate with peroxide oxidation. After understanding their characteristic and ensuring to preserve the fluorescence, we have to test their antimicrobial efficacy. We do so by comparing their minimum inhibitory concentration. So the lower the MIC value, the higher the efficacy. We use Alamo Blue assay to test this. Here, the resozurin dye, it is a low fluorescent dye and is visually seen as blue color because it is absorbing other colors except blue in the color wheel. So when cells are respiring, they oxidize NADH to NAD+. This oxidation reaction causes the reduction in the resozurin dye to become resorufin. And this is a fluorescent dye, which can be visually observed as pink color. So these fluorescent properties can be used for quantifying bacteria when we're studying with spectroscopic studies, but we're not doing it here. So we're only doing the visual observation. Here is the representative figure of Alamo Blue assay, starting at a metallic zinc concentration of 2000 ppm. So, and it's serially diluted. So here is 2000, 1500, 250, and so on. So pink indicates the bacteria are still alive, and we're seeing the lowest concentration where it is still blue. So this is the concentration at which the bacterial growth is inhibited. We tested on commonly studied human pathogen E. coli and plant pathogen Xanthomonas alpha-F and Pseudomonas syringae. Xanthomonas alpha-F is a citrus canker surrogate. Pseudomonas syringae, it causes bacterial speck. We have untreated quantum dots here as control. So the sample's efficacy differ with different bacterial strains. For example, if we're looking at HPT2, it is not as efficacious in E. coli as in syringae. But we do see the consistent strand that with increasing peroxide concentration, there is better antimicrobial efficacy in all three strains. So this may be due to that with conversion of zinc sulfide to zinc sulfate, there are more available zinc ion for killing. Since the application is in field trial, there is a chance that these material might come into exposure with humans. So we want to test its cytotoxicity to find out safe concentration. For this, we use human dermal fibroblast cells. So this is the skin cell. It is a common model system to study cytotoxicity, and it's also a first-line defense in human. We tested 4 metallic zinc concentration, the highest being 100 ppm. Generally, the material is considered safe if they show above 80% viable cells. So we see that HPT1 and control didn't show cytotoxicity to the highest concentration tested, and HPT2 up to 50 ppm retains 80% viable cell and appears to be non-toxic to HDF cell. HPT3 is most cytotoxic among them, so this is not preferred system for field trial despite of their antimicrobial efficacy. Also, they have no fluorescence. In conclusion, hydrogen peroxide oxidized the zinc sulfide shell to zinc sulfate, confirmed by XPS. Fluorescent intensity and antimicrobial efficacy are dependent on extent of oxidation. HPT1 and HPT2 samples show enhanced fluorescence compared to control, while HPT3 is quenched. Antimicrobial efficacy increased with higher peroxide concentration. HPT2 is a sample of choice for further studies because it retains strong fluorescent property, exhibits 1.2 times increased intensity than control, and it is antimicrobial, also has low cytotoxicity. So up to 50 ppm, it shows 80% viable cell. Further study, plant uptake and translocation study of synthesized quantum dots. We can further study that with SCM and EDX on plant cross-section after the treatment. If there is a zinc ion concentration higher than control, it is an indication that these quantum dots are delivered inside the plant. Or we can also use the fluorescent lifetime imaging, so flame imaging, to rule out quantum dot fluorescence against the plant background. Here are my references. And thanks to Department of Chemistry, Nanoscience Technology Center, MISA, and Office of Undergraduate Research for funding this project, Mr. Kirk Scammon, Material Characterization Facility for XPS data, Dr. Santra's group member for all their supports, especially Ali Aljan for mentoring me on this project, Mikhail Yang for the cytotoxicity study, Nirav Moda for MIC study, Tyler Maxwell for helping me build skills for this project, and Dr. Centra for all the feedbacks and directions. Thank you very much.